Okay, welcome back. I hope you had a very engaging coffee break, and it's a pleasure to introduce Jose Maria Ezquiaga. He's a professor at the Niels Bohr, assistant professor at the Niels Bohr Institute, and he has been for the last 2 years coordinating the LIGO lensing group together with Otto Hanoksela, who is here or will be here soon. Hi, nice meeting you. And he's going to give an overview of lensing of gravitational waves. And he said it's fine to ask questions during the talk, so please go ahead.
Yeah, thank you, Miguel, and thank you all for being here. I think it's really exciting to have a conference on this topic. And I think, as Miguel was pointing out also in the introduction, it's really impressive the amount of work that has appeared in the last years, and certainly this field is like booming. So I think it's good that we are here, and also because I think also there are plenty of observational but also theoretical open questions that I think we can together work out. So of course, when if we are here thinking about gravitational waves, is that because these are new signals that are providing us a completely new perspective of the universe. And this is something that when we think of gravity, it's very particular because we are observing compact objects that orbit around each other until they merge. And they produce these perturbations of space and time that travel throughout the universe for billions of years until they get in our detectors. This is something which was long anticipated and is a consequence of our modern understanding of gravity being a dynamic space-time. And I think what I really hear, so of course, I'm sure you all have seen this kind of plots. This is the amplitude of the gravitational wave as a function of time. This is the in-spiral phase of the gravitational wave. Then the compact objects are close to merge, and then they rain down as it was being mentioned in the previous talk. I think to me, of course, the signal is beautiful, but what is fascinating is the lower panel. When you think that we are talking about objects which are about 30 times the mass of our sun, which only within a couple of tens of kilometers are moving at the speeds close to the speed of light. So I think this is fascinating for gravity being able to probe this strong field regime. But also, I think gravitational waves are fascinating for cosmology because they naturally are giving us a way to look to the distant past. So a very schematic way of seeing this is with this diagram, where you are seeing in the radial direction, that's the time since the Big Bang. So we are here at the center, 13.8 billion years after the Big Bang, which is supposed to happen in the exterior of the circumference. All these little dots are just possible places, times where stellar mass black holes could merge according to what we think reasonable astrophysical models are. So what you see is that these compact objects are merging throughout the history of the universe. And what is remarkable is that we are already reaching a good chunk of them. And in the very, very near future, we are going to essentially measure all of them. So here, this dotted line schematically indicate how far we can detect these signals. And I'm going to be a bit more quantitative later. But just to give you a sense that right now, we are essentially being able to observe a few billion years back in time. But with current detectors, in only a couple of years, we're going to already improve a lot. But in the next decade, with next generation detectors, we are essentially going to be able to observe all the binary black holes merging throughout the history of the universe. And just to put this into perspective, we are talking that the first detection of gravitational wave was in 2015. Here we are talking about 2035, 2040. Just in a couple of decades, we are essentially passing from the first detection to being able to observe everything. And for me, that I've been thinking a lot about cosmology. This is also fascinating because you are probing the universe in periods where it was very different to how it is now. So now we are in a universe dominated by dark energy. But if you move a few billion years back in time, dark matter dominates. And of course, also, as you all know, and one of the reasons that we are all here in this conference is because it's not just that the universe is expanding, the universe is full of galaxies, structures, all these dark matter distributions are going to affect our gravitational waves, and that's what we want to see in this talk. So the era of gravitational wave astronomy is here. We have 4 detectors which are operating across the globe. So far, from the first 3 periods of observation, we accumulated about 100 events, which include binary black holes, binary neutron star, and also neutron star black holes. So this is very much to say that gravitational wave astronomy is a reality. And even so, we are all at this very time, we are taking data. So the 4th observing run is still ongoing. If you scan this QR code, you can go to the public alerts, and then you can make a setting so that you get a message in your phone from the universe whenever there is a gravitational wave. And that's very cool. You can get up to the latest event. And if you go to this website, you will see something like the list of current candidates. We have not yet finalized our analysis of this 4th observing run, so they are still candidates and not confirmed events. But what you see is that already we have about another 150 events or so. So data is coming, and that's really good. So to put this into a more quantitative perspective, here on the left, this is the number of gravitational wave detections as a function of time. The first detection in 2015, and then we accumulated about 100. We are now here almost at the end of 2024. This, by the way, these shaded regions is just projections, just given the observations that we had, what we think we will get. And here, these are the first 3 observing runs, the 4th, which is ongoing. And then on the right, this is a more quantitative version of the plot that I was showing before. This is telling you how far you can detect these signals in redshift as a function of the total mass of the binary. So what you see is that we are most sensitive to binaries of about 100 solar masses. So that's, for example, if you have a 50 and 50 solar mass binary black hole, you could get potentially up to redshift of 1. With current sensitivity, most of the cases is quite a bit below that. But anyhow, this is what is coming next. So I think we are now in an era in which we are really enjoying getting these events every couple of days. But very fast, we are going to move to a regime in which we're going to get thousands of events per year with current technology. But then with next generation detectors, we are going to get events every hour, events every few minutes. And when you think of these, the cosmological aspects, that's the plot on the right, you essentially see that you can get to redshift of more than 10. So that's going very far. Yes. Could you remind us what's Yes. Thank you. And I tried not to put many acronyms, but I forgot to mention it. So ESI is just a concept that is supposed to be based in where the LIGO detectors are, but it will use new technology. And then XG is an acronym for next generation detectors. So this could be either Einstein Telescope in Europe or Cosmic Explorer in the US. This also, by the way, reminds me that here, this plot, it's only speaking about ground-based detectors. There is also a mission, LISA, that is going to be put on space and has been approved by the European Space Agency. That's detecting black holes at much higher masses. Yes, please.
Since you've been interrupted. I see that now it's below where it was predicted. We're getting less than we saw, certainly in binary neutron stars. So, a factor 3 maybe, or more. How safe is to extrapolate to 35 when we already know we're not getting the wrong numbers?
Well, I think the so always we do. So we have data. We analyze this data. We build models that represent this data, and those models have uncertainties, and that's what we are. What this is supposed to represent. Of course, what happens is that here you see that our current detectors. I mean, we are not sensitive by any means to mergers past redshift of 1. But however, when you think of how these black holes could be formed, and you think that these that's a
source. We're talking about surely there are sources. The point is that right now we can't see what we thought we could see.
My point was that we don't know yet what is the population at higher redshifts. So what I mean is that, of course, there is an uncertainty, and when I'm making these plots, this is extrapolating that a model at redshift past 1. So of course there is an uncertainty here in what we know. As you point out, in the case of binary neutron stars in particular, it's sad to say that we were very lucky in the second observing run to get a multi-messenger event, but the rate actually after that has been dropping. For the case of binary black holes, actually it's been very stable, and we are just narrowing down pretty much the error bars. But it's a good point to bear in mind that here, so this is a statement about our detectors. This is a projection that includes some assumptions about the population of compact objects. So here there are assumptions. This is just projected sensitivity. But thanks for the question. And please, people feel free to interrupt anytime. Is that clear? Okay, so what I wanted to put into perspective for the question of lensing is that in particular, if we are thinking, for example, of these gravitational waves being lensed by galaxies in the universe, then what you would expect is that from what we know from electromagnetic observations, that this should happen for between 1 in 1,000 or 1 in 10,000 events. So this is just a very schematic, but this is to say that we are entering in the regime in which we expect to see some of our events to be in lens, and this is just thinking of lensing by galaxies. And then the other aspect that we will talk in the talk is that when you observe lensing, you can magnify these signals, and effectively magnifying your signals essentially is allowing you to see farther away. So if you think of our current sensitivity, which is 0.4 here, if you have a signal that is magnified by 10, and I will define what that is, already you go to past the sensitivities of 0.5. If you magnify by 100, which is something unlikely but could happen, then you go to next generation detector. So lensing in that way, this is something that certainly in the electromagnetic spectrum is how it is. It's a way to access the very distant universe, and in our case, it's going to be a shortcut to next generation detectors. So the plan for today is that I just want to give the beginning some kind of more theoretical framework in terms of why we can do this kind of studies for cosmology and lensing with gravitational waves. That is to say that gravitational waves are standard science. And then I will put a bit of the math that goes into how we understand lensing in general. And I will do that because that's relevant for the context of gravitational waves, because there are certain differences with electromagnetic lensing. And then I think the main part would be go over current searches, what are we looking into the data, what we have seen so far, and I will finish with some aspects that I think are interesting for the future in different ways, like substructure, wave optics, and multi-messenger, and other things. So here in this QR code, you can get the slides for the talk. Maybe later, I don't know if this will be also circulated to the participants. Just before I get into the topic, to say that this is supposed to be an overview, so I'm going to try to be pedagogical and also simplify many things, and certainly I will probably forgotten many of the relevant references, but when possible, I have tried to point to different people that would be speaking in the room. They would be speaking in this in the conference who are here in the room. So please ask me, but also ask all the good experts that are here. Great. Okay. So I want to start just by reminding ourselves of why we can do cosmology with gravitational waves, why we think of these signals as being standard science. And this comes from a couple of facts, but I think are important to remind ourselves. So we were seeing these compact objects which are merging, that emit a signal that then propagates through the universe, and then we detect. The fact that we can learn about cosmology from these signals comes in the very first place from the fact that general relativity predicts how the signal should look like, and that we understand that signal. So we can, when we look at the data, and this is the strain data for the first event, we know why this is wiggling in this way, and we have robust numerical, first principle results of how the signal should look like, and also numerical relativity simulations that predict how this signal should look like. I'm making this emphasis because that's not the case at all in general when you think of transient astronomy. When we think of fast radio bursts, when we think of short gamma ray bursts, when we think of even supernova, those are very complicated events from which we have a good understanding, but I would argue that is more complicated. Certainly in the case of binary black holes, this is something that I think for the most part we understand very well. And then the other aspect is that throughout this propagation, just through the background cosmology, the effects on the gravitational waves are very are very simple. Just our signal is going to scale with the inverse of the luminosity distance, and then the masses of the binary are going to be stretched by the expansion of the universe. So we have signals that we understand how they are emitted, we understand how they propagate, and then, of course, the last step is that we need to understand how those are detected. And this, we do so just by understanding very well our selection function. So that is, we take, for example, templates. So we take models for the waveforms with different properties. This is the template bank that we use in terms of the component masses. So you see that goes from 1 solar mass to 100 and even further. And we are able to put these signals into our detectors and see if we detect them. So we build a detectability for different type of waveforms so that we can then, when we observe a signal, we can go back to the properties of the source because we understand to what ranges we detect. And this is also what you were seeing in the previous plots of the horizon distance, the fact that for different masses, we were seeing farther or closer. That's another reflection of the fact that for different, we understand our selection function and that this depends on the properties of the mass. So when we get a signal, in simple terms, we get the strain, which is the amplitude as function of time. But from this strain, you also see the frequency evolution as a function of time. So this frequency evolution is what we call the chirp. One second. And from this chirp, essentially what we are inferring is what is the mass of the system. So how much, what is the frequency evolution of the system? Yeah, there was a question. Yes, so this is just because this is what we actually use in our searches. And then when you use these templates in the searches, as you go to higher masses, is not so, the signals are shorter. And then with less points, you can essentially recover the same kind of signals. As you go to smaller masses, the signals are very long, and then even smaller changes in the parameters is going to make that your waveform is different, and that's why you need more templates. That's a very good question. More questions? Yes?
The figure, the value of spin is limited to 0.98. Is there a special meaning to that number? Why not 0.99 or something like that?
I don't know exactly. Something to say, just because you talk about the spin, I think that's a relevant quantity, and especially when you have asymmetric masses, when you have systems with the masses are not equal, spin can play a very important role and can modulate the signals. So that's something which I think, I was simplifying a bit the picture, just saying that we understand everything perfectly. If you have some of the effects of the spin, this is still active, an area of active research, but yeah, I see two hands.
Just a quick comment. I think this comes from the ability of numerical relativity to produce a waveform. I don't think you can go much higher than that.
Yeah, thanks. You were going to say the same?
It's just, I think in this case specifically, it's the model is not tuned to any higher than this because of the NR waveforms.
Yeah. I mean, from the astrophysics perspective, I think we would say probably this is more than enough. But anyway, so what I was saying is that from the chirp, we get the masses, and then once you know the masses, in the previous formula, there was some distance and mass from the amplitude. So this means that from the amplitude, we get directly luminosity distances. So these are the kind of elements that we need to do cosmology. And then I think the next important step is just to remember that for gravitational waves, it's only gravitational interactions that can modify this picture that I'm showing here. So what I was showing before is just the propagation of gravitational wave in a background cosmology. The only other thing that is going to change the propagation of gravitational waves in general relativity would be interaction with massive objects. And that, again, I'm making the emphasis to distinguish from electromagnetic radiation, where you need to worry about dust, you need to worry about the scattering with electrons, you need to worry about the intergalactic medium. That's something which I think is special of gravitational wave. Of course, gravitational waves are more rare, are difficult to produce, but when they are produced, they are really, really good probes of the underlying cosmology and the large-scale structure in the universe. So that was just to get a sense of how we think of these signals. I want to now put a bit of math just to think of the formalism for lensing. And I guess just before that, remind ourselves that, lensing is ubiquitous in the electromagnetic spectrum. Essentially, if you look far enough, you're going to see things which are being lensed. And it can actually be really impressive. You can get multiple images of distant quasars, or you can even get galaxies which are completely distorted to form these arcs and rings. So lensing, especially in the strong lensing regime, can be pretty dramatic. So to study lensing of gravitational waves, what we need to do is to solve the propagation of our gravitational wave in a curved spacetime. And then what we want to do is we want to do a mapping between the properties and the location of the source to the observer through the frame of the lens. So doing that, we need to take this equation and we need to set some background. So what we, I'm sorry, maybe I should have said, of course, gravitational waves are linear perturbations on a curved space background. So when you think of that, you have already done that decomposition. And then what you need to think next is how you are going to model the background. And then for us, we are going to be thinking of cosmological setups where there is some gravitational potential. So here, this A is the scale factor. It's just telling you that the universe is expanding. This is in conformal time, but it's not relevant. The important thing is that the metric is going to be perturbed by this length that you have here. So if you take this metric and you insert it here, you're going to get actually a lot of terms. You can get things which are not so easy, but throughout this talk, and this is, I think, something which is one of the main points, I guess, of discussion of this conference, is to go beyond this approximation. But here we're going to be thinking of weak field limit. So we are going to be thinking of being far enough from the gravitational potential so that it is small. So in other words, we are not going to be worrying about the structure, the horizon, if we are thinking of black holes. We are going to be far away from that. And that's a very important simplification, because when you do that, your equations simplify dramatically, and you essentially get effectively a wave equation of this type, where you see that you only have this correction from the Newtonian potential. The other important thing is that in this approximation, the gravitational wave, which has two polarizations, both of them are going to propagate in the same way and are not going to be affected by the lensing. This is something which I think Julia and Hayato are going to talk about how to go beyond that when you include strong field effects that could change and induce spin effects. But for my talk, both polarization propagate in the same way. So once you have that, what you can do is that you can take the previous equation and then you just go to Fourier space. So then what you are introducing is these frequencies here, omega. And then what is the final assumption is that we are thinking about systems which are in a cosmological setup. So typically, the size of your lens is going to be much smaller than the distance from the observer to the lens or the distance between the lens and the source. So this is what is known in the community as the thin lens approximation. What means essentially is that instead of, you can think of lensing happening exactly only at the distance where the lens is. So you can only think of, instead of the lens being a volume, you can think of it being contained on a plane. So what is, you can take this equation and you can find the solution in its integral form. So this is normally done by introducing this amplification factor. So your lens signal, your solution in frequency domain, I should have put here a tilde, sorry, is going to be your initial signal, your h tilde, times your amplification function. And this amplification function is going to be an integral of this plane in the image plane. So it's a plane because of the thin lens approximation. And then what you find is that this is the integrand is the exponential of the time delay surface. And here I should have also included that the time delay surface is a superposition of the geometric time delay, just the fact that the waves don't follow straight paths, and also the Shapiro time delay, just the fact that when you travel through a gravitational object, you feel the gravitational potential. So for the context of gravitational wave lensing in the weak field limit, essentially all of our problem is to solve this equation. In general, what this is telling us is that we need to follow, you can interpret this equation as integrating over all the possible paths that the wave could take from the source to the observer. So there is also a very nice analogy from this formalism with path integral formalism in quantum field theory. Is this clear, by the way? Do we have questions so far?
Theta S.
Yes, so that's sorry, what do we have theta S? Here, yeah, sorry, that's the source position. So, yeah, and that's again just a vector because we are only, yeah, that's the source position.
So is it a three-dimensional vector or two-dimensional?
No, two-dimensional vector. Yeah. More questions? Yes.
This is not in the geometrical optics approximation here, right?
I'm gonna just move to that now. So this is the general framework. Well, sorry, are there other questions before I move to that? Okay, so this is the general framework that you need to solve. And so in general, this means that you would need to follow all the possible paths. That's not always the case. And that's why. That's because for many cases, your integrand is going to be highly oscillatory. So you can think, for example, here, your frequency, if you have a high frequency, as for example, you have always with electromagnetic radiation, that terms is going to be, that exponential is going to be very large. The exponent is going to be very large, and then the exponential is going to oscillate a lot. So that's a problem, actually, that is also very well known. That's also what happens in quantum mechanics when you go to take the classical limit. You also have to take the limit of the stationary phase approximation, which essentially means that from all the possible paths that the wave could take, you are only going to form images in the stationary points of your integral. So this mathematically means that you need to take this time delay, and you are finding the points. And sorry, the notation here, this small t is just the time delay surface with dimensions, and theta is just the x, but with dimensions. But anyway, the important thing is that you need to find the stationary points of your system, and those are going to define where the images come from. So then what you can do is you can take your time delay surface and you expand around these points, and then you're going to have a first order contribution. The first time derivatives, by definition, they vanish, and then the next correction is second time derivatives. These second time derivatives are going to give you a contribution that is a Gaussian integral that one knows how to solve, and actually what they are going to define is the magnification of your signal. So this first term is going to tell you the arrival time of your images. This second time derivatives tells you about how much they magnify or not. So when you are in this regime of where the stationary phase approximation is valid, that you can also represent as the time delays between the stationary points times the frequency being a large quantity. Essentially, what happens is that your amplification function from this general integral collapses into a sum over all the possible length events that you have, and each of them is going to be corrected by a magnification, a difference in the arrival time, and a phase. This phase here depends on the type of solution of the lensing potential, and can have different values, 0, 1/2 of 1. But you can also map this phase into the parity of your images. So for example, if you have a lens and then you have a source, which is this dinosaur, then if you have a type 1 image, essentially you are preserving the parity of your image, and you could, for example, magnify the image. When you are thinking of a type 2 image, what you are doing is you are essentially just flipping this image over the axis of the lens. And when you have a type 3 image, you are flipping it once and then flipping it twice. So these type 3 and type 1, they have the same parity, but the type 3 has been flipped twice, and then the type 2 has different parity than the type 1 and type 3. So this is something that, for example, with galaxies, I mean, if you were to know you can see these differences in the parity of the signals. Okay, yes, please.
Is this phase shift always a half integer in this business?
Yes. Yeah, and that you can solve because it's very simple. Just when you're doing the Gaussian integral, depending on the signs of the eigenvalues, you could have two positive eigenvalues for your Hessian matrix, or if you have plus and minus, or both minus. Okay, great. So now I'm gonna move towards the searches. And essentially, we're gonna be thinking of two regimes. Well, as always, we think of our source and our detector, but we're gonna think in one regime in which the lenses are big. That could be galaxies or clusters of galaxies. And then in those regimes, essentially, we will be concerned to the possibility of producing these multiple repeated chirps of the original signal. So that's when the stationary phase approximation is valid. And then there's going to be another regime when the stationary phase approximation is not valid. And then you are not having repeated chirps of the original signal, but rather you have interference between the different paths, and this leads to distorted waveforms. So this is, broadly speaking, the two categories of signals that we are thinking about. So for the first case, if you take the math that we just did and you plug it into the fact that the basic properties of the gravitational waves, what you find is that essentially the magnification is going to rescale the luminosity distance of each of the repeated chirps that you get. So they will have different magnifications, they will have different arrival times, and they will have different phase. However, when you think of the frequency evolution that you detect in your observer frame, that is not going to change. So the detector frame masses are not going to change. However, if you are analyzing an event, and then you are not taking into account lensing, and then you are thinking, okay, let's compute the source frame masses of this system. The way you do it is that you take your detector frame masses, and then you divide by 1 plus c, where the redshift, you get it from the luminosity distance. So if you were to have a signal that is being lensed and you don't know, then your luminosity distance is going to change. So if it's magnified, you're going to think it's closer. And then if you think it's closer, then you're going to think it's more massive, because then your detector frame mass is the same, but your redshift is smaller. So that's another way. I mean, from when you are inferring the source frame masses, lensing can change them. But it's important to remember that actually the observable that you have is not being changed. So the frequency evolution does not change. And I think there's going to be some discussion of it. Yes.
Can I ask a question? So is there any kind of telltale sign that would allow us to identify the signal is being lensed? So kind of sharp signature, or this can be kind of masked through the noise? So
yes. So hopefully I'm going to argue that there are a few of them. Yeah, it's a great question. Of course, the key here is how, I mean, we get some of these signals. How do you know this is actually are coming from the same source, or these are just independent gravitational waves? Yes, I'm going to come back to that. Other questions? Yes?
I think this analysis is correct if you assume that all the source and the lens and the observer are static. If they're in motion, there might be also some kind of frequency effects involved.
Yeah, that's a great point. And I think actually there is also going to be a talk about that by Johan Samsin. For example, if you think that there is some peculiar motion of the sources. Yeah, thanks for pointing that out. Okay, so what we get in our what we would get in our detectors is repeated signals, repeated chirps of the same signal. And I think, again, something which is important is that with gravitational waves, we are and this is, I mean, this is just a simulation, but what we are observing is coherently the phase evolution of our signal. So this is not like when we are looking at electromagnetic radiation that typically we just have the intensity. Here we are seeing the phase evolution. And this is important because if you have two repeated copies, then what you can do is compare if the frequency evolution of the two, the phase evolution of the two, matches with each other or not. Something which is important also to remember to compare with other electromagnetic observables is that with gravitational wave, arrival times are measured exquisitely. So we can measure this to milliseconds. So for us, knowing when a signal arrives, it's very easy. So that's something that if you are interested in time delays to do astrophysics or cosmology, that's something that we do very good. However, what you care is where the images would be located in the sky and you want to resolve that, with gravitational wave, you are not going to do it. Just because if you think of the Einstein radius of a galaxy produced by a galaxy that is 1 gigaparsec away, that's 1 arc second. And when you think of localization errors from gravitational wave, that in the best cases, a few square degrees. So for us, for all the purposes, the signals are going to be coming from the same region of the sky. And that's something that we are using in our searches to see if those events are lensed or not. So what you can do is, for example, you can, yes, please.
100 observations, have you observed some clustering or not? Or is it just depending on the legal arrangements? Or
Clustering of...
I mean, the orientation where these events go in the sky.
Yes, so everything is consistent so far with being
isotropic, but that's also not surprising given our sensitivity. As we improve, what you would expect is that these signals will trace the largest scale structure of the universe, but that will be mostly because of weak lensing and not because of and also because of the sources being produced in the large scale structure.
Yeah, but we have not observed. It's an interesting question.
Yes. So can I go back to so this localization error? This is assuming one single detector and network of detectors. How does it?
Sorry. This is maybe just so. This is the Einstein radius. This is the image separation. So this is what it comes from, just from the lensing. Here I have not put in numbers what we do with our with a network of detectors, but you can think of with 3 detectors, you could expect like a few square degrees if the signal has some reasonable signal-to-noise ratio. So a few square degrees is much bigger than this Einstein radius of half second. So that was always my point. Yeah.
Okay, so you can think, for example, you can take 2 events, and then you can you can plot the right ascensional declination, so that's its position in the sky. You can plot its observed masses for the M1 and M2, and then this, for example, looks like something that could be consistent. So this is 2 events, blue and green. They are overlapping with each other. But of course, the question is, how do we go from things like this to assess the significance? Yes, please.
The difference between those 2 events is like huge, no? Is it even possible?
Yes. So this is January is the first event, and the second one is in August. Yeah. So if you are thinking of an astrophysical system that would produce this time delay, would have to be a cluster of galaxies. So you would need to have a lot of mass in that system to make a time delay of several months. Yeah. So that's also something which is you are hinting at, which is a good point, is that we have, because we understand also the a bit of the properties of the lenses, we can have some astrophysical priors to what we should expect in terms of time delays and also in terms of magnification of the signals. So that's something that you can use in your searches. So far here, I'm not using any of that.
So I guess the point here is that you have things like this, but of course, if I tell you like which of these is being lensed, it will be very difficult to say. This is on the left, just 2 simulated lens events. On the right, this is just 2 simulated random events. And this is for the sky localization, but you could also have similar things for other properties. So just by random chance, different events will have similar properties. And when you are looking at pairs of events that could come from the same source, then there is a problem, because the number of false alarms of things that could look as something that is lens is going to scale with the number of pairs. So you're going to have a lot of things that could look as being lens. So the whole game of the business is to find strategies to fight these false alarms. And there are different ways in which one can do it. But one important thing is that because we have with a catalog of 100 events, you compute n squared divided by 2, more or less that's your number of pairs. So you have a lot of pairs that you need to analyze. So you need to have pipelines which are fast. So within the LIGO, Virgo, and Kagra collaboration, we have kind of like different tiers of pipelines. Some of them are faster, like the ones I'm presenting here. And then we have also some a bit more involved ones. But one of the first things that you can do is just simply compute the overlap of your posterior distribution. Or you can also use some machine learning, and Johnny, who just left, I think will speak about this in his talk. So you can get some of these statistics that tells you, for example, for the catalog, you can see what is the false positive probability. Something that I just want to emphasize as well is that one can, I was thinking in terms of properties of the parameters of the binary, but one could also think that with gravitational wave detectors, actually what we are measuring well is the phase of the gravitational wave as a function of frequency. That's our main observable. From that, we do parameter estimation and we get masses, spins, distances, but in its essence, what we are just observing is the phase evolution. This is the phase in the Hanford detector as a function of frequency. This is for the first event. And you see here that the error in the phase is a fraction of a radian. So the phases that we measure with gravitational wave detectors are very good. So one possible strategy as well to fight these false alarms is to look for the consistency of the phases that should be the same if they are lens events, except modulo for this pi-half phase shift. So if you have this pi-half phase shift, that's going to shift your phases, but you can account for that. And this is just simulated data of how this would work. But just to say that you can also fight the false alarms with some of these. Now, at the end, what we do in our analysis is that we do what we call a joint parameter estimation. So we take this pair of events and we analyze them jointly, thinking using the lensing hypothesis. So what does this mean? So this means that you have these two events, but you are inferring the properties, fixing that their masses should be the same, the distance should be the same, modulo the magnification of each of them, the spin should be the same, the sky localization should be the same. So for example, if you think of a sky localization, and this is a plot from this paper here, from Rico, who is in the audience, you see, for example, you have one image which is localized with 31 square degrees. You have a second image. Sorry, the first one is the blue. The second one is the green, that is larger, 80 degrees. And then you do the joint inference, and then you get something which is like 17 square degrees. And that's because you have assumed that these two events come from the same sky location. So just from the fact that you have two events arriving at different times, effectively is as if you were to have more detectors to measure the same signal. The nice thing of having this joint parameter estimation is that you can do Bayesian model comparison. So you can compare the evidence of this pair of events being lens with the evidence of this pair of events just being random realization of an underlying population. So you can get quantities to measure the consistency of the events with each other, and you can also get, if you put some priors about the properties of the population, you can get some base factor that is ultimately what will tell you if this pair of events is likely to be lensed or not. This is in principle actually all you need here, because base factors should tell you the answer, is this likely to be lensed or not. However, in practice, it's a bit more complicated just because also this process is computationally costly. Your base factor is sensitive to your astrophysical priors. There are a bit more difficulties here. Something also to take into account is that when you have these multiple images, some of them could be the magnify. So this means that some of them could be buried in the noise of your detectors. So there are also strategies to do searches for these subthreshold events. Now, in terms of this catalog of 100 events, we did analyze in the search for these repeated chirps. And this is a summary plot of the base factor that I was mentioning for different assumptions in the population model. And these are different pairs of events. The point to make here is that this is a base factor of 1. In all of the cases, the base factor is less than 1, which means that we find that the lensing hypothesis is disfavored. So we don't see any evidence of repeated chirps in our data. If you don't see repeated chirps in our data, then what this means is that you can put constraints on the properties of your population. And for example, you can constrain the merger rate of binary black holes. So I'm gonna speed up a bit, but for example, for your question of are there signatures that are unique of lensing, one of them actually is, for example, these phase shifts, because our gravitational waves are not only one frequency mode that is evolving with time. Actually, our gravitational wave is a superposition of different frequency modes, different higher modes that evolve with time. So if you lens your signal, you get the magnification, you get the arrival time, and in the case of type 1 images, you don't get any phase shift. However, when you have type 2 images, you have this pi-half phase shift. So this pi-half phase shift is something that is affecting all of your modes, but then relative between each other, the phase shift is different for each of your higher modes. So what this means effectively is that you are shifting in a different way the phase of each of your higher modes. So overall, your gravitational wave waveform could also, the shape could also change. So what this means is that there are characteristic modifications of the waveform that come directly from this phase shift. This is unfortunately a small change that will require higher signal to noise to actually be detected, but it's one of these things that I think is very clear that if we observe that, we will think this is being lensed. The other point that I think is interesting is that in this mapping, when you are solving the propagation of gravitational wave, I was talking about this Hessian matrix as the place where you get the magnification of your signals. What is interesting is that this Hessian matrix has some singular points when you have point sources. So what this means is that there are regions where you get magnifications which are infinite. So if you think of, for example, a pool, these places with bright, where the sun is brighter, that's just where you are focalizing all, these are the caustics that you are seeing. Anyhow, what is interesting is that when you think of these caustics are interesting because they exhibit some universal behavior. So for example, as you approach to the caustic, the relative magnification scales inversely with the square root of the distance to the caustic, which at the same time scales with the arrival time. So what this means is as you get closer to the caustic, you're gonna get two images which are very magnified with a very short time delay. And that's something which I think it's very unique. And what this also means, by the way, is that as you are approaching, the caustic, the time delay is getting smaller and smaller. So at some point, the stationary phase approximation that I was mentioning is going to be broken, and that's going to set a maximum magnification. So diffraction is going to eventually regularize this divergence of the lensing map. But what this, you can think, for example, of galaxies, and as you approach to the caustic of the galaxy, what you are gonna start seeing is that you're gonna get overlapping signals. So this is work led by Rico, who is here in the audience. This is the signal to noise a function of time. Details are not important, but for example, seeing this kind of overlapping signals with delays of a fraction of a second, I think it's something that is not expected, at least astrophysically. I'm going a bit faster just because I want to finish covering the things. Please later ask me more questions. But the other very, very, very interesting regime, of course, is of that of wave optics. So when the time delay between the stationary points times the frequency is not a large quantity, but rather of something of order 1. And you can think of the time delay, for example, for a point mass, it scales linearly with the mass of the lens. So if you have a lens of 100 solar masses, this is essentially 4 milliseconds. So this is, and you can think here that the frequencies of gravitational waves is hundreds of hertz. So this also gives you a sense of what are the masses in which you're going to get relevant interference effects for current searches. So wave optics is going to happen when these two quantities are comparable. And you could also, if you go to the very low frequency limit, at some point what happens is that your wavelength is so large that it stops seeing the lens, and then your amplification factor just goes to 1. But the case of wave optics is interesting, and then in that case you need to solve the integral for the amplification factor, and you're going to get these really nice diffraction patterns. Here, this is as a function of frequency, and this is the impact parameter, so how much you are aligned with the position of the lens. If you take this is something which is known analytically for a point lens mass, and you can see how this will affect, for example, the waveform of your signal. So if you have a time delay between your stationary points, which is small compared to the duration of the signal, you can get some distortion, but maybe not so big. But then for certain regions, certain values of these time delays, you can get, you see the orange here has a shape which is very different from the blue, which is the not lens waveform. So there's been a lot of progress and there's in solving this diffraction integral, and I think Hector will tell us more about this. The one point that I wanted to make is that within the collaboration, of course, we search for these kind of signals. We have codes to do that, and we can also make Bayesian model comparison to see if we think an event is lensed by a compact lens or not. Something which is important is that when you are looking for distortions of your waveform, you should also make sure that there are not noise artifacts in the data, and also that the waveforms that you are using are stable for that kind of event. If you go to the catalog, then what you see is that we essentially get something for the distribution of our base factor, which is very much consistent with a background of not lens events. So this is something that for us indicates that there is no evidence of lens events. And from this non-detection of lens events by compact objects, then you can, for example, put constraints in the fraction of dark matter objects. Fraction of compact objects, which are a relevant fraction of the dark matter. Something that I want to emphasize, though, is that these constraints that I was mentioning here assume that your search pipeline is able to detect this distorted waveform. That's actually not guaranteed. So this is, I think, a very important work of Yuno Chan, also from the Niels Bohr, but not here in this conference, unfortunately, where he actually did a search with using the same search pipelines that we use in the LIGO Virgo Cara collaboration, and simulate lens events, and then the end product is this false alarm rate that tells us when an event is being when an event is detected or not. So if you have a false alarm that is smaller than 1 every 6 months, essentially that's what we categorize in our catalogs as something being an event. And what you see here is that for many lens masses and impact parameters, this false alarm rate is much, much bigger. So what this means is that with the current templates that we have, we could be definitely missing some of these lens gravitational wave. So this is something that we certainly need to improve. I think I probably don't have, how much time I have? 5. Yeah. Yeah, so I'm just gonna highlight what I was thinking are interesting aspects. I think many of them are gonna be covered actually by other talks, so that's great. Just so that you get a sense, and you can also ask me later in terms of these future prospects, things that I think are interesting. And I think the first main point is that gravitational waves are point sources. So what this means is that they are probing the gravitational potential in a very fine way. So you are, in other words, very sensitive to small scales. So for many purposes in lensing, in the electromagnetic spectrum, you could just think of your lens as being like isothermal sphere, and you don't really care about the fact that galaxies actually have substructure. But for gravitational waves, actually, this is something that can be much more important. And I wanted to highlight quickly the work of Luka Vujeva, who is here also in the audience, studying the case of clusters of galaxies. So this is, for example, the 3 different clusters of galaxies, and this is the magnification maps in the image plane and the source plane. This is the source plane, this is the image plane for the 3 of them. And you see that these systems are rather complex and definitely not a sphere. So what you see, for example, when you analyze the distribution of time delays and relative magnifications, is that things deviate very much from what you would expect from just having a sphere, which is this shaded region here, and actually can go over all the place. So this goes, for example, to the question of, can we use information of time delays to know what is the type of lens that is lensing my system? And this kind of study hints that it's going to be difficult. So you could just, clusters of galaxies could have most of its time delay being much smaller than what you would expect, and mimicking regimes that a single galaxy could produce.
Spot the source location?
Yeah, this is the source location. So you are putting sources here. Yeah. And this, of course, also applies for the case of dark matter subhalos. And I'm not going to say much because Trusty, I think, is going to speak about this. But the main point that I want to highlight is that when you are thinking of subhalos, and those subhalos are making some wave optics distortion in your waveform, what is interesting is that you are sensitive to lensing beyond the Einstein radius. So typically in a strong lensing, you think of the area in the sky where I'm going to have effects that I can measure, and that's typically dictated by the Einstein radius, which in this plot would go from the impact parameter of 1, because this is dimensionless. So here, this is the relative uncertainty in the measurement of the mass of the lens. And then you can see that there is, you can measure effects of lensing for impact parameters which are beyond the Einstein radius. This, of course, depends very much on your source, the signal to noise, but I think that's something which is very appealing of looking for wave optics, the fact that you are in principle sensitive to higher regions. And also, just to say that this substructure also can make your signals being more magnified. So if you look at the plot of the magnification distribution, for the simple model, that's the gray. For these cluster models, you could get more magnification. Multi-messenger is another avenue which I think is exciting, and Graham will talk about it. Just to say that in wave optics, so when you have multi-messenger, it could happen that your gravitational wave is actually in a wave optics regime, while your electromagnetic radiation is going to be in the geometric optics limit. And what this makes is that your phase velocity that you infer from the gravitational wave could make you think that your signal is traveling faster than the speed of light or faster than the electromagnetic radiation, and that's just because your waveform is distorted. No information is traveling faster than the speed of light. It's just that the distortions should be taken into account. And I'm going to skip over this. And the final point that I want to make is that I was at the beginning, I was talking about the fact that we are about to get the first detection of strongly lensed gravitational waves. Then you see here, after that, there is a whole regime in which we're going to get hundreds of thousands of events. So this means that we are going to get hundreds of lens events, or if not thousands. So this is also, for the future, I think, a very interesting area where you can do statistics with your lens gravitational waves, and you can use that to learn about the population, but you can also use that to learn about cosmology, and Jit, I think, is going to speak about this. And the final thing, sorry, Miguel, is just to say that I was mentioning that only lensing within general relativity, only lensing could modify your waveform so that it doesn't look like a waveform that is being unlensed. So what this means is that if you get this signal that is being lensed and you are running some test of modified gravity, you could think you can get false violation of general relativity just because you are getting something that doesn't look like an unlensed general relativity waveform. So I think that there should be, and I think it's happening, so it's not something that I'm concerned, a dialogue between people studying lensing and also people doing a test of general relativity. So thank you so much. I'm happy to take more questions and also during the coffee breaks and lunch. Thank you.